It's a little hard to believe, but this is the final lesson of the final unit of Math 30. We will not be learning any new content after today. Once again, tomorrow we will be reviewing for this unit. I haven't decided. I think we'll probably have a little quiz tomorrow, and I'll let you know what it's about. The Monday we get back from our Christmas break, we will be reviewing a little bit more, and then that Tuesday we're writing the unit exam. That leaves us 7 days of classes, and then the 8th day of classes would be your diploma exam. And in those 7 days of classes, kind of right smack dab in the middle, there's the English 30 and the social 30. And again, how many of you are writing English? So that day is shot. I mean, I will be here. I will be helping people here with review materials if you're here. How many of you are writing social 30? So that day, I mean, a lot more people are here. I'm assuming with the crazy schedule that they've developed, assuming you do not have a final exam on a particular day before our diploma exam, you really should be here. Okay? I think it's going to be the Monday, a week from the Monday that we get back, we write our in-class exam, replacement exam. And I don't like having something like that on a Monday, but the Tuesday and the Wednesday, I believe, are those diploma exams. So it is what it is, and we can't change it. We're going to be looking today at something called the Binomial Theorem. We're going to be solving problems involving the Binomial Theorem. And the Binomial Theorem allows you to easily expand any binomial power of the form x plus y to the n. So if I write x plus y to the 10, which means x plus y times x plus y 10 times, at the end of this lesson, you should be able to write out what it's equal to. And it will not be a matter of multiplying everything out. There are shortcuts. It doesn't have to be x plus y. It could be 3x minus 5y to the 6. It could be p squared minus 10 to the 4. What's important is the base of this power is a binomial, and the exponent of this power is a whole number. It's 0, 1, 2, 3, 4, etc. We cannot use the binomial theorem for fractional exponents, which is going to cause a bit of a problem when we try to apply this in calculus, if you're in my calculus class next semester. So if I asked you to do this, and I'm going to click fairly quickly through this, you're not going to write this down. What this means, if I wanted to keep you busy for the next hour, maybe that's an exaggeration, is I would say, you need to multiply x plus y by itself 7 times. And how this would be accomplished is you would group those two and multiply them out. If I multiply x plus y by x plus y, I get x squared plus 2xy plus y squared. And then you do the same there, and you do the same there, and then this guy just goes along for the ride. So now you're down to, instead of 7 things to multiply together, you're down to 4. So you could take these first 2 beasts and multiply them together. Now, what would be involved in multiplying those together? Well, you would use the distributive property. You'd take that x squared times the x squared times 2xy, x squared times y squared, and you'd move on to the 2xy. And you would multiply that 2xy in the first by everything in the third. You're with me of what's going on here, but we don't want to do it. And we're not going to, but I think this gives you a motivation as to why the binomial theorem is important. And then, I guess we could do the y squareds and move on to the second pair. By the way, what you're going to get here, I'll show it to you in a second. Then move on to the second pair and start multiplying everything through. In principle, you know what you would have to do. I hope you understand that the likelihood of making a mistake is very high. It's very easy to mix things up here. That's what you would get for the first pair, and that's what you would get for the second pair, and you would repeat. You're not going to do this, right? As a spectator, you would lose interest, which you probably have already. And as a person doing it, you'd probably go, maybe I'll watch something on Netflix instead. Okay? So using the binomial theorem, I can come up with this in I can write the first step in the expansion in about as long as it takes me to write from left to right, and then I can clean it up and get the final answer. I can do both of those steps in about a minute, easily. 2 minutes if I'm going slow, 30 seconds if I'm rushing. It's not tough at all. Even something like 3x minus 2y, which is not x plus y. Well, it kind of is. It's just that our x is 3x and our y is negative 2y. Raised to the 6, I can come up with the answer to this. It's going to take me a little bit longer because of that 3 and that 2. But it's not going to take me long at all. So how do we figure this out? Well, I'm going to go through this chart that's on the front page, and these are going to be all of the binomial expansions of x plus y to the n for n equals 0 through 4, except you have on your chart all of them written, and then it says or for each one, right? I've blended these two together up here, and you will see what I mean. So this is what's on the left-hand side of your chart. I'm just saying x plus y to the 0 is 1, and we should all know that a base raised to the 0, as long as the base is not 0, is 1. X plus y quantity to the 1 is clearly x plus y. And x plus y squared would be x plus y times x plus y, and if you FOIL it out and simplify it, that's what you get. And the spacing here is a little odd in between the terms, because I'm blending the second part of your chart, the part on the right with the part on the left, okay? How would you get x plus y cubed? How would you determine that? Well, you would take x plus y squared and multiply by x plus y and do that distributive thing, okay? But you can just trust me that x plus y cubed gives you that, and x plus y to the 4 gives you what's written there. I want you to notice that for the first one, x plus y quantity to the 0 could be written this way. And don't ask why. In fact, if you didn't even notice that, it wouldn't matter in your understanding of the binomial theorem. But I could write it as 1 x to the 0, y to the 0, which is what's written on the right-hand side of your chart, right? I also want you to notice that all of the first terms in all of these have a coefficient of 1. And when you write out x plus y, you don't write 1x plus y. You typically write x plus y, but we could put a 1 there. And similarly, all of the last terms, we could put a 1 in front of them. And now I'm going to really start adding a whole bunch of stuff that's unnecessary. For example, all of these x's and y's that are not squared or not cubed or not to the 4th, they could be written as x to the 1 or y to the 1. You're still with me? And even though there's no y in this first term of x plus y quantity squared, I can put y to the 0. So if you look, for example, at the x plus y squared on the left-hand side of your chart, all it has is x squared plus 2xy plus y squared. But I'm saying if you want to, you can put all of this extra stuff that is not usually looked at. Similarly, all of those last terms contain an x to the 0. What we're focusing on right now, by the way, are the variables and the exponents, and you're not worried about these other numbers, the 4, 6, 4, or the 3 and the 3. We'll get to that in a bit. So, how many terms are there when we expand x plus y to the n? This is a fairly important thing. Well, if you take a look at this first one, there's one term, isn't there? And there's 2 terms there, and 3 terms there, and 4 terms there, and 5 terms there. When you look at the exponent on the binomial power, in the first one it's 0. And in the second one it's 1, and in the third it's 2, and 3, and 4. And the point is that if n is 1, you get 2 terms. If n is 4, you get 5 terms. The answer to this question is the number of terms will always be n plus 1. And again, we're limiting ourselves to n being a whole number. We would use different ideas in mathematics if they were fractions or if they were negative numbers or negative fractions. Everybody's clear on where I'm getting the n plus 1 from? Okay. What is the behavior of the exponents in all of these binomial expansions? Well, if you take a look at, I'm just going to start with, let's start by focusing our attention on, we're going to look at to the 4 in detail in a bit, but let's focus our attention on this line. That's not the line I wanted. Let's focus our attention on this line. The exponent in the binomial power is 3, and when you look at the exponent on x in the first term, it's 3. And when you look at the exponent on x in the second term, it's 2. And when you look at the exponent in the next term, it's 1, and then it becomes x to the 0. So I'm talking here about the following. I'm talking about the fact that that is a 3, and then it goes down by 1, down by 1, down by 1, and we're out of x's. Whereas at the same time, simultaneously, the y starts off with nothing, and every time x goes down by 1, y goes up by 1. It's like it's handing off one of the exponents. So we can answer this question by saying T1 has x to the n and y to the 0. Always. The first term will always have x raised to whatever the exponent on the binomial power is, and it will have no y's. T2, the second term, will have those for the exponents. Now, if you're confused about the n minus 1, all I'm communicating, although it's a deeper meaning, is that whatever the exponent on x was in T1, it's 1 less. And the exponent on the second term will be y to the 1, or the exponent on y in the second term will be 1. The third term will contain x to the n minus 2 and y to the 2. I want to do one more before we draw this question to an end. The fourth term, if there is a fourth term, will contain x to the n minus 3, y to the 3. And before I draw this to a conclusion, because we still have to talk about what happens at the end, I want you to notice that the number you're taking away from n for the exponent of x is the number that's the exponent for y. And we'll go through this in detail with a different example in a second. But these two numbers are the same. I could even put up top here for the x to the n, y to the 0, I could put x to the n minus 0. Right? And what happens is this continues until the last term will contain x to the 0, y to the n. And this is just the best way to write this out. I think it's the best way to write this out using mathematical language rather than using English, because English we would say the first term has the exponent of n and it keeps dropping by 1, while at the same time y keeps increasing by 1 from 0 until you're out of x's and all of the numbers are on y. You get the point though, right? Okay. Predict the variable components, so we don't know what the coefficients are going to be, of the expansion of this. Well, the first term will contain x to the 5, and although we don't need to write y to the 0, we could. By the way, we do actually know what this coefficient is, don't we? hopefully you've discovered by looking at that table that the coefficient of the first term in x plus y to the n is 1. And then it's just a matter of saying plus. Now you have to, well, I have to. You've got lots of room. But up here, based on the size of my writing, I have to space things out right. I know there's going to be 6 terms because n is 5. So the second term will have a number times x to the 4 times y to the 1, and you certainly don't need to write the 1. The next term will have a coefficient times x cubed y squared. The next term will have a coefficient times x cubed y to the 1. The second to last term will have a coefficient multiplied by x to the 4. Whoops. Whoop, 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 whoop. One of the things I'm going to tell you is after you write things out, you should always go back to the beginning and check if x starts at the beginning and goes down by 1 each time. So this should be 2 and 3. And then we're going to have x to the 1, y to the 4. And then we're going to have 1, x to the 0, y to the 5. And I'm going to double check. I always double check with the binomial theorem. I'm going to take a look at this 5, and I'm going to see if it goes from 5 to 4 to 3 to 2 to 1 to 0. I'm going to take a look at this 0 and see that it goes to 1 to 2 to 3 to 4 to 5. So that's it. This is just giving you practice with looking at the exponents and finding out the variable terms, the variable parts of the terms. So how do we find the coefficients? This is the only reason I believe why we put this in this unit. The coefficients are combinations, it turns out. They can be found using combinations. And on the next page, I'm going to walk you through x plus y to the 4 and what everything is. When you take a look at your next page, so we're looking now at page 25, it's all filled in, but I don't think you're going to learn by just me reading that with you. I have to show this to you visually. This is what x plus y to the 4 is, and you can trust me on that. If you take x plus y times x plus y times x plus y times x plus y, you will get that. So each coefficient is a combination. And the combination is what we call n choose k, where n is the exponent on the binomial. So the first coefficient is 4 choose 0. Just think about this for a second. You can use your calculator at any point during this exploration. But doesn't it make sense that 4 choose 0 is 1? How many ways can you choose nothing out of 4? One way. You just don't choose anything. It turns out that this is 4 choose 1. And you shouldn't need a calculator to know that 4 choose 1 is 4. If I have 4 people, how many ways can I choose 1 to go for ice cream? 4. It turns out that this is 4 choose 2. 4 choose 2 is 6. Does anybody play crib? The reason why 4 of a kind is worth 12 points is there are 6 pairs in 4 of a kind, and each pair is worth 2. If you don't play crib, that was just gibberish. Okay? This is 4 choose 3, and this is 4 choose 4. Notice that we're starting at 4 choose 0 and going to 4 choose 4. If you look at my fingers, 4 choose 0, 4 choose 1, 4 choose 2, 4 choose 3, 4 choose 4 gives you one more term than the number 4. It gives you 5 terms. So those are all of the coefficients. It's always going to be n choose k, starting at 0 and going up to n. Are you with me here? That the n in the first part is always the exponent. So when I ask you what is n when we calculate the coefficient of the first term, or what is n when we calculate the coefficient of the third term, n is the same for all of the terms. But k is a different number for each term. K is a parameter. I call it the key number. I don't see that written anywhere in text, but I like the word key because it starts with the letter K. Obviously, this is not a vertical shift. Okay? And each term has a different value of k. What is k? K in the first term is 0. The second term has a value of k of 1, 2, 3, 4. What we notice is this. The first term has a k value of 0. This is crucial. The k value will always be 1 less than whichever term you're interested in. So t1, the first term, has k equals 0. t2 has k equals 1. If I said we had a binomial expansion where there were 100 terms, the k value for the 90th term would be 89. That's really, really important for you to be successful in applying this. And this is k equals 2, this is k equals 3, and this is k equals 4. And again, if you count off the numbers 0, 1, 2, 3, 4, you get 5, which is why we have 5 terms. The exponent on y is always equal to k. That's k. That's k. These numbers for the exponent on y are always the value of k, always. The value on x is n minus k. Now that's not maybe the best way to think of it, but if you look at n minus k, that's what this number is. If you take, looking up here, 4 minus 0, you get 4. For the second term, if you take n equals 4 minus k equals 1, you get 3. This is the way it's typically shown to people. However, what this really means is the two exponents have to add up to n. Right? These two things must add up to give n. 4 plus 0, 3 plus 1, 2 plus 2, 1 plus 3, and 4 plus 0. Which makes sense because we started off with x being to the n and y to the 0, and it's just a trade-off one exponent at a time. So the total number is still going to be n. That's it. So if I look at example 1, which is still maybe part of the warm-up, what are the coefficients here? Well, this coefficient is 5 choose 0. This will be 5 choose 1, 5 choose 2, 5 choose 3, 5 choose 4, and 5 choose 5. And you notice that we start at 0, we end at 5 for k, that's k, and that gives us 6 terms. I think I know these, but I could be wrong. Is this 10? And by the way, this is 10 as well, because if you choose 2 people to go for ice cream out of 5, it's the same as choosing 3 people to leave behind. Which explains why these coefficients are always symmetrical from beginning to end. And then it's back to a 5, and then it's back to a 1. Okay? All right. So what is the 5th term in this expansion? What we're going to do here is the following. We're going to say that we are comparing x to 2x, and we are comparing y to negative 3y. And we have to go away from writing the first, second, third, fourth, fifth. We have to graduate away from writing the first term and then changing the exponents and changing the exponents. If we want the 5th term, I'm going to put it up here. If we want the 5th term, then k is equal to 4. And we know that the coefficient, I'm leading up to something which maybe will make you happy or not, I don't know. I prefer to do this type of problem the way I'm going to do it, and then in a minute I'll say you could have done it a different way. I know that the coefficient is always n. N is 7, right? Doesn't matter whether it's the first, second, third, fourth, fifth term, whatever. N is 7, x is 2x, y is negative 3y. So I know that the coefficient of this term, in terms of what we've learned, is 7 choose 4. It's n choose the key number. I know that there will be x's and there will be y's, and I know that the exponent on y matches the key number. These two things always must be equal. And I know that this is going to be a 3 because the two exponents have to add to give 7. Can somebody please tell me what 7 choose 4 is? Owen, do you have it already? 35? Can I get a seconder? 35. So we get 35. This means 2 to the 3 times x to the 3. This means negative 3 to the 4 times y to the 4. So when I said a minute ago the coefficient is 7 choose 4, I said the coefficient based on what we've learned is 7 choose 4. But do you see that since x and y have numbers associated with them, that's going to build more to the coefficient. The coefficient of this expression is going to be this times this times this. The variable component will be x cubed y to the 4. So you need to figure out for me what 8 times, this is 81, negative 3 to the 4 is 81, times 35 is. And I might as well just grab my calculator and do the same thing. $22,680. And if you were to expand out 2x minus 3y to the 7, which is more complicated than that x plus y to the 7 that I showed you with all the curvy lines, because of the negative and the 2 and the 3, that's what you would get for the fifth term. So this is what's going to make some of you happy, and some of you, you will shy away from this like I do. I don't use this. This is a formula that's on your formula sheet. It's saying that the coefficient of a term is n choose k, the exponent on y is k, the exponent on x is n minus k, and I will tell you why some of you won't like it, and it's why I don't like it. I don't like it as a teacher. I know that confuses some students. But we just found the fifth term, didn't we? Can you tell me what k is for the fifth term? Forget about this formula. What is k for the fifth term? It's 4, right? Well, if you put this 4 here, you get p5. That's all it's saying. It's saying that k is a number less than, by 1, less than the term number you're talking about. So you can always use this formula. When I use it, I typically don't make reference to the k plus 1. I just say the fifth term is n choose 4, y to, x to the n minus 4, y to the 4. All right. What is the sixth term in this expansion? I highly recommend making a list of what n, x, and y are for every term. When I look at this and I say n is 9 and x is 3x and y is negative 1 over x squared, I hope you can appreciate why I put quotes around the x and the y. Those are the statements for n, x, and y for the first all the way up to the 10th term. Doesn't matter which term we're talking about, we use those things. But for T6, which is what we're after, we use k equals 5. So if you want to look at that formula that's right above this example, you can. I'm just saying it's T6 equals, and if you use the formula, k is 5, so when you put 5 in, it's 5 plus 1 for the subscript, you'll get T6. I've learned that it's always n, choose the key number times x, which we should put in brackets, raised to an exponent, this is the way I do it, raised to an exponent that I save for the end. You can do it right now. You can put 4 here if you want. But I just say times y, which is negative 1 over x squared, which is kind of a weird thing. We're calling it y, but it's really in terms of x. This will be to the key number, and then I say this exponent must be 4, because 4 plus 5 will give me the 9. Is 9 choose 5 120? No. 126? 126. So 126. This will also contain a 3 to the 4 as part of the coefficient. It will also contain a negative 1 to the 5 as part of the coefficient. What I'm doing is I'm extracting all of the constants and just writing them out in front for you. It will also contain an x to the 4, and I'm being awfully liberal with my use of brackets here because sometimes they're needed and sometimes they're not, but why not just cover your bases and put them all the time? And then we will also have a 1 over x squared to the 5. I'm not a fan of using negative exponents at this stage of the game, but I could write this negative 1 over x squared. I could write it as negative 1 x to the negative 2. And that means I would have negative 1 to the 5 and x to the negative 2 to the 5. Okay, I could use negative exponents. And sometimes you might want to. So now I figure out what the coefficient is. The coefficient of this beast will be whatever that is. And then over here, we end up with one over x to the 6, a kind of basic math 9, math 10. After going through logs and exponents, this should not be a big deal. 1 over x squared to the 5 is 1 over x to the 10. We have x to the 4 over x to the 10. Cancel 4x's as factors on the top and the bottom, and you get x to the 6 on the bottom. And the coefficient will be negative 10,206, because that negative 1 raised to an odd exponent will be negative 1, and then times the 81 times the 126. So I would probably just write my answer this way. I forgot what that was. Negative 10206. Good? Yeah.
Wouldn't it also be, or wouldn't it be positive because the y terms would be negative?
No. So, y is negative. Y is negative 1 over x squared. I am not claiming this is y. That's not y. What I have done is I've taken this, I have taken my y raised to the k, and I've said that negative 1 over x squared all to the 5 is the same as negative 1 to the 5 times positive 1 over x squared raised to the 5. So that negative in the line that I've got the blue stuff highlighted in the second line there, that negative is no longer on the 1. That is no longer y to the 5. It's just the variable part of y to the 5. Does that answer your question, Hunter? Okay, good. All right. A couple more examples. I think that went well, and I think you should be able to determine a term. 6th term, 8th term, 5th term, 2nd term, whatever. This is a little bit different here because you were not told which term we're after. If you knew I'm just going to throw out a number here. If you knew that the term that involves b cubed was the fifth term, you would know what k is and you could answer the question. If you knew that the term that had b cubed was the seventh term, then you would know that k is 6 and you could answer the question. So the problem becomes different to begin with. Which term has b cubed? Now the reason why this is tricky is because x contains b's and y contains b's on the bottom, so when you multiply x's and y's together, you get some canceling happen. So this is one way to do this. It's to make a chart and to explore this, and tomorrow I will go through an algebraic approach, but to explore this just using common sense, that the first term will contain b squared to the 9. Everybody just contemplate that for a second. That the first term is going to contain b squared to the 9, and it's going to contain over b's raised to the 0. Just like Hunter, our conversation that we had, I am not even looking at the negative and the 3 here. I'm talking just about the variables. Do you agree that b squared to the 9 times 1 over b to the 0 will not give you b cubed? It's going to give you b to the 18. And I've painted myself into a corner here. This is going to give you b to the 18. That's not b to the 3. So we know it's not the first term. What about the second term? Well, it's going to contain 1 less b squared and 1 more 1 over b. And this will be b to the 15. Just run that through your brain. B squared to the 8 is b to the 16, and we're dividing by b to the 1. I'm just going to throw this out, and I hope it sticks for most of you. There is a reason b is decreasing in terms of the exponent by 3. And it's because every time we move forward, we have 1 fewer of these, so we lose 2 b's. And we have 1 more of these, so we lose another b because we're dividing by another b.
Shouldn't it be 3 over b?
Once again, if you look at the top of that table, it just says variable. I don't want to worry right now about the coefficient part. So that 1 over b is not y. It's just the variable component of y. And when we need to use that negative 3, we're certainly going to. Okay. I mean, you could put in the negative 3 and not just say variable. You could figure out what the first term is, and you would have to also include 9 choose 0 and 9 choose 1, but it's not helpful really at this point. If we do one more, this term will contain b squared raised to the 7, and it will contain 1 over b raised to the 2. 7 times 2 is 14. 14 minus the 2 we lose here is 12. But you can see the exponent's going down by 3. And if you understand that, you shouldn't even need to do the third term. You should be able to just continue this table until you land on b cubed. That's all. I'm going to be writing awfully big because I started writing big. You can write smaller, obviously. The fourth term will contain b to the 9, 3 fewer b's. The fifth term will contain b to the 6, 3 fewer b's. The sixth term will contain b cubed. Jackpot. That's what we are after. We're after the term that has a b cubed in it. And all of this that we've done here, all of this that we have done was done solely for the purpose of identifying the particular k value. That's the only reason we did all that. We know that the term we're after is k equals 5. That came out wrong. The term we're after has a value of k equals 5. All of the terms use n equals 9 and x equals b squared and y equals negative 3 over b. So now, Jeff, is the time where we throw that negative 3 in, because now we're going to answer the question. This term will be 9 choose 5 b squared to the 4 negative 3 over b to the 5. The answer to the question is going to be whatever 9 choose 5 times negative 3 to the 5 is. Everything else, we can, if we have confidence, we can say everything else is going to be b cubed. And it will, right? B squared to the 4 is b to the 8. And then we're going to divide by b cubed. That will be we're going to divide by b to the 5, which will give you b cubed. So when you work out those constant components, how embarrassing that I don't remember what 9 choose 5 is. 126. We just did that one. Times negative 3 raised to the 5. I'm putting the negative 3 in brackets because I'm using my calculator. I wouldn't include the negative. I know that the answer is going to be negative because 5 is odd. So what this term is negative 30,618, and it works out to be a b cubed. So the coefficient is negative 30,618. That's it. I know there is one more example, but I don't want to spend class time doing it, other than to say that if you were asked for the constant term in this, that means you were after the term that has x to the 0. How can you possibly get x to the 0? Because it's a combination, literally, it's a combination of x squareds and negative 1 over x's, and you're going to end up with some mix in there that gives you x to the 0. How many of you see that the first term would contain x to the 12? And that the second term would contain x to the 9? Not because it always goes down by 3, but it will in this case, because you lose an x squared and you gain an x to the negative 1. You're losing 3. So all you would have to do is keep going until you figured out 12, first term, 9, 6, 3, 0. It's the fifth term, which means k is 4, and you'd find the answer to the question. They can get a little more tricky, but again, I have to make a decision here in terms of what I'm doing in class that gives you enough tools to be successful if it gets more complicated. We just don't have time to get into more complicated examples.